Hello everyone, my name is Cameron Reyes, and today, me, alongside my partners Brandon and Andres, are going to be discussing our ME106 Mechatronics project. First off, I'd like to give you guys a little bit of some background on our project. The problem which we are trying to solve with our design is the fact that oftentimes in airports, many people may struggle to carry their very heavy luggage around. This may be due to numerous things, such as disabilities. Maybe they are stuck in a wheelchair and they can't carry their luggage around, or maybe they don't have the strength to carry it around because of old age, or maybe it might even just be because of convenience sake because we as humans are lazy. So the goal of our design was to create a scaled down prototype of a motorized luggage carrier, which will allow the user to be able to maneuver and carry around their luggage easily wherever they need to go throughout an airport. So, first off, our original design consisted of three wheels, two wheels being in the front, which are both motorized, um, almost like a Segway, to allow for movement, whether that be left or right, by making one wheel stop moving and the other wheel keep turning. And the same would be true going the other way. And if it wanted to go straight, obviously both wheels would move at the same time. A third wheel was also put in place more as a way to balance our mechanism, was a way to balance our design. And that wheel is not motorized, it is just on a swivel. Are designed a little bit to use solely ultrasonic sensors for the process. So basically, if a person were to be on towards the right ultrasonic sensor, it would shift right, and if the person were to be on the left side of an ultrasonic sensor, it would shift left, and if a person were to get too close to the ultrasonic sensor, it would stop. This can be seen more in the code, which I will talk about next. So the main thing I helped out with in this project was the coding in Python and in Thotty. So first off, to run down our code, we first started off by initializing all the different pins. From there, we created functions which had to do with duty cycles and max cycles. So like it would get the percentage of the duty cycle that we wanted to use. In case it was about to run into something, then maybe we'd slow down a wheel or make it go faster, and so on and so forth. Uh, Next, the last part of the code is the while loop part of the code. And this code was basically how it would maneuver around. So when there was when there was nothing on any of the ultrasonic sensors, nothing in the way of any of them, and the distance was farther than 400 for the ultrasonic sensor, it would just go straight. It would move forward. If the left ultrasonic sensor was to have something within a proximity of less than 400 in front of it, it would start turning left. Therefore, if you were to move in front of the ultrasonic sensor, the ultrasonic sensor would follow you left. The same can be said true about the right side. If something was within 400 of the right ultrasonic sensor, it would start shifting right. This would be done by obviously stopping the left wheel to make it shift left and making the right move, and the opposite would be true for the right side, where the right wheel would stop moving and the left wheel would turn. That being said, also, if you were to get too close to the middle ultrasonic sensor, then the entire thing would stop because there's an obstacle in the way. Lastly, I want to state what I've learned from this project, and I feel like the biggest thing is integrating those ultrasonic sensors with our motors and being able to use them simultaneously together and in a way that made it easy for the user to use our device. Lastly, I'd like to say that I learned that all about the design process for projects in general, and how exactly those phases worked, whether that be like a testing, whether that was like figuring out what we're going to do, then a testing phase, then finally like actually putting that all into action.
Okay, so here at our J1 connector, we have this white pin here for our power. It's supplying 5 volts to the IR board, and we have our orange pin that's our frequency selector pin. So when this is brought high, it'll tune the board for 10 kilohertz signals, and when it's brought low, it'll default to a 1 kilohertz signal. Our yellow pin here controls the exposure of the IR sensors, and then we have our red pin here that resets the the counter to 0. So this will bring the active sensor back to 0. And moving over to the J2 connector here in the middle, can't really see very well. Oh, hole right there. So you see right here where I have the pointer at, that's our ground for the board. And then to the left of that, we have our, what we believe is the analog output of the board. And panning out, I'm going to move over to the main board, Pico. So here we have our yellow exposure wire going to GP7, our reset wire going to GP7, our frequency selector is on, let's see, GP8, and adjacent to that we have all of our motor controller direction pins. So we have green for IN4, which is counterclockwise, blue for IN3, clockwise, purple for IN2, which is counterclockwise, and finally gray for IN1, which is clockwise. And moving on to the other side of the Pico, we have our 5-volt out, which is this white pin right here. And then moving forward, we have this gray wire or gray pin, which is on GP26, which is our ADC pin. So we're reading our analog output from the IR board to the Pico at this pin. And then adjacent to that, we have our ground for the board. All right, and moving forward, we have our L298. And so we have our enablers for motor A. So motor A is our right motor, and motor B, which is this white wire here, is our left motor. And those are connected to the right motor's enabler is connected to GP16, and the left motor enabler, motor B, is on GP17. And then, as you can see, we have these wires kind of tucked away down here, but these are the positive and negative leads that are wired to our DC motors. And then in the corner here, in the corner between our Pico and our L298 motor driver, we have a buck converter, so DC to DC buck converter. So this is taking our 12 volt voltage from this 12 volt 1.3 amp hour solid sealed lead acid battery, and it's bringing the voltage down to 5 volt USB, which we then have a USB cable here connected to our Pico, so we can provide power to the Pico independently of a computer. So this cart is able to move on its own as long as it has the program uploaded to the, or flashed to the Pico. And we have let me take this out. So this is a Duracell 12 volt 1.3 amp hour battery that we are using to power all of the sensors and the motors on the cart. All right, and that concludes the hardware section.
Hi, so my name is Andres Cisneros. I'm going to be talking about the drive system that we've used. We have 2 DC motors that we've been loaned out, thanks to Professor Furman. So due to budget constraints, we've decided to go with this style of mechanism that we created out of materials that we bought at our local hardware stores. We've decided to go with a belt drive system, as we can see here. We've used foam wheels to allow something that can take more weight versus a rubber or any other types of wheels that we could find. These were really sturdy and can handle the weight of the cart, along with pretty much everything we've been able to put on it. We've had to construct, again, due to budget constraints, we had to use a metal plate, but it wasn't thick enough, so we had to make it more rigid with an extra plate, a thick plate in the back that allowed more rigidity of the plate that holds the whole drive system together. I've done this. The shaft for the wheel had to be extended out, and what it was able to do to make it steady so it wouldn't flex side to side. I was able to use bearings in order for the movement to have free rotation movement while still keeping the structure together. Otherwise, if this bracket wasn't here with the bearing, this would just, as soon as we laid in the position of where it would actually run, this would flex way too much and not run properly. And yeah, that's it for now.
So I'm Brandon Chang, and I'm going to be talking about the sensors we used on our motorized cart. So the heart of our primary sensor is going to be the E10 IR board, and so it uses a series of 8 IR receivers that receive a tuned signal. So this there's a frequency selector integrated chip that can either be select 1 kilohertz is tuned for a 1 kilohertz signal or a 10 kilohertz signal, depending on whether or not the frequency selector pin is brought high or low. For low, it'll be default 1 kilohertz signal that will be received by the IRs, or it'll be a 10 kilohertz signal. Now, when the sensors are cycled, 1 through 8, and it begins a new cycle, the sensor or the IR board will cycle to high sensitivity mode, which automatically changes the frequency selector to high, and so it'll then be looking for 10 kilohertz signals if there are no like sensor data being received when you're running through the first cycle when it's a low sensitivity. And so, moving on to our obstacle avoidance system, we have 3 ultrasonic sensors, one for the front, one at a 45-degree on the right side of the cart, and a 45-degree on the left side. Now, these have a 3.5 meter range and a 1 centimeter resolution. For obstacle avoidance, this is good enough for our purposes. However, for our project, we ran into issues where we're being able to read any analog data from the IR board. So we had to repurpose the obstacle avoidance system to demonstrate the integration of sensors, hardware, as well as our drive system. So we repurposed them for the purposes of stopping whenever obstacle got too close, but also once the obstacle is read from a certain distance away, the cart will then go in that direction. And then if in an intermediate distance, if the cart senses that the subject is moving to the left or to the right, the wheels will then correct to go into that direction. All right, and that concludes the sensor section.
So here we see that the sensor in the middle stops it. Removing your hand should allow both wheels to turn. Blocking these two allows the right wheel to turn. Center should stop. Activating both sensors on the side allows both wheels to turn again. Blocking these two should allow the right wheel to turn. Taking hands off and leaving it in the center, blocking the middle, should allow both to stop.
And that completes our project overview. Thank you for watching. Please leave a like and subscribe if you want to. Thank you.